may be multiple ways to get to a location, and there will be a tie as to which route a router might
Was
choose.
good, my
Fortunately, there
niggas?
are ways to
Whoops.
break the tie
Take
within
those,
the
take those,
router, and
good
in this
cover.
video, we'll look at a number of ways that tie-breaking process might occur. Let's look at a routing table. This is a routing table I pulled from a Cisco router, but it's almost identical in form and function to routing tables that you would find in a workstation, in a server, or in any other manufacturer's router. In this particular example, this routing table was built based on a number of networks that were directly connected and routes that were received using the RIP dynamic routing protocol, specifically RIP version 2. If we look at the routing table, the top part of this routing table is a legend that gives us more information about the codes that are used within the routing table itself. In the bottom is the routing table, and you can see that the first set of letters on each one of these lines corresponds back to a different set of codes that are shown in that legend. For example, you can see the first line of this routing table starts with the letter C, which means that that particular route is directly connected to this router. If we want to see the route that was added using RIP version 2, then we need to find a line that starts with an R. And indeed, there is a line that has an R, which means that everything on this line was created because of information that was received by this router using the RIP version 2 dynamic routing protocol. And you can see there is a lot of information contained within this line. You can make out some IP addresses. There are different values such as 120/1, and it does appear there are even counters here along with information about specific interfaces. Let's break out just this line of information to determine what is contained within this line of a routing table. Let's break out this line of information to see which each one of these provides. We know that that first R at the beginning of the line is the route code, and if we refer back to the R in the list of codes, it does say that this was received using the RIP protocol. The next one is 10.10.30.0/24. This is the destination subnet that has been added into the routing table along with a prefix link of /24. We also have the 120/1. This is actually two different values. The 120 is an administrative distance. We'll learn more about administrative distance in a moment. And the next is a metric. We'll also talk about metrics in this video. You can also see that it's via 10.10.50.2. This would be the next hop or the destination that we would be sending this traffic if we needed to go to this particular location. We also have this time value. This is a timestamp that tells us how long this route has been active inside of this routing table. And in this case, this route has only been active for 14 seconds. And lastly, you can see the outgoing interface that would be used. Sometimes this interface is included, sometimes it's optional depending on the routing protocol or the router that you're using. It's sometimes nice to see that this particular next hop is one that we would reach by going out a specific physical interface in that router. So when the router is making its routing decision on where traffic should go, it's evaluating everything in this routing table to determine if this would be the best possible route to use to forward this traffic along to the next hop. One of the first things that a router is going to evaluate is where this particular traffic is destined. We need to be able to look at the destination IP address and compare that to the subnet IDs and prefix links that are contained within the routing table. If there's a match, then we'll know where to forward this traffic. This means that this IP address range and prefix link becomes an important consideration when we begin to forward traffic. We need to look at both of those together to determine if this is the best possible route for this traffic. And if you were to look at a routing table, you may find that there are multiple routes listed to a particular subnet, but there might be different prefix links in each one of those lines. So you might need to evaluate each individual line of a routing table to determine which one is the most specific for this particular route. For example, let's say that you need to communicate with a device that's located at 192.168.1.6, and your routing table has 3 different routes that would match that particular IP address. One of them is 192.168.0.0/16, the other is 192.168.1.0/24, and the third is 192.168.1.6/32. All of these would be valid routes to that particular destination, but only one is the most specific. We need to evaluate not just the subnet ID, but also the prefix link to determine which one of these is the most specific for that particular destination. And if we were to look at 192.168.1.6, we would know that 192.168.1.6/32 would be the most specific route. In fact, that is the most specific route because a /32 is specific to an individual IP address, in this case, 192.168.1.6. Now, if this route was not in our routing table, we would have to choose between 192.168.0.0/16 and 192.168.1.0/24. The /24 is the more specific route than the /16, so we would choose the middle route if we had a choice between those two locations. This can get even more complicated if your routing table happens to have identical routes to a location that go to different next hops. How do you know which next hop would be the correct one if everything else was identical? And the one way that you would be able to make that determination is by examining the administrative distance. Different routing protocols are assigned different administrative distances within the router itself. This allows the router to pick the best route based on the type of protocols or the type of information that it has received. For example, if this is a local connection, it is physically connected to the router, this is the best possible way to get to that subnet, so it has an administrative distance of 0. As you can see here, the lower the administrative distance, the better the route might be. If you have manually configured a static route, the router assumes that you must be the most knowledgeable person for that particular route, so static routes have an administrative distance of 1. If this route was added to the routing table using EIGRP, the administrative distance is 90, and if you receive this route via OSPF, the administrative distance is 110. You can see that other dynamic routing protocols and methods are listed in this table with the appropriate administrative distance for a Cisco router. In some cases, the routing protocol itself may be in a position where there might be duplicate routes to a particular location, and the routing protocol has to make a decision on where the best route might be. In that case, we would want to look at the routing metric to be able to break that tie. Routing metrics are an internal value that are used by the routing protocol itself. So BGP has its own set of routing metrics, OSPF has a completely different set of routing metrics, and EIGRP uses its own set of routing metrics as well. This means that you can't compare routing metrics across different routing protocols. The routing metrics used for BGP are very different than the routing metrics used for EIGRP, and there's no way to compare or contrast those routing metrics across routing protocols. But similar to an administrative distance, BGP might create its own set of routing metrics to a particular site, and then it can determine what the best route might be based on its own internal set of routing metrics. For example, the routing metrics for BGP might be 1 or 2. It will choose the route for 1 because that is the lowest routing metric.
Oh,
let's look at our routing table.
What a nasty pants.
Have that one line in the routing table, the 10.10.30.0/24. It has an administrative distance of 120 because it is RIP version 2, and it has a routing metric of 1. RIP uses the number of hops to a location as its routing metric, so we know that this particular destination is 1 hop away. To be able to reach that particular network, we would go to 10.10.50.2, and we would get to that particular location by sending this traffic out serial 0/3/1 on this router. If you were to use a different routing protocol, for example, EIGRP, you would have a very different routing metric. Here is the same routing table to the same location, but we've enabled EIGRP instead of RIP2. You can see this line in the routing table was created with the code D, and if we refer back to our legend, we can see that D does refer to EIGRP. Everything in this line is very similar to what we saw with RIP version 2, although you'll notice the administrative distance is different. It's a 90 because EIGRP has a higher priority in its administrative distance than RIP version 2. But you'll notice that the routing metric that is determined by EIGRP is very different than the routing metric that we saw for RIP version 2. RIP version 2 uses the number of hops, whereas EIGRP has a completely different calculation that it uses to determine what the best route might be. As you work more with routing tables and begin evaluating these routes on the fly, you'll become much more comfortable with determining where the best next hop might be for a particular packet. One of the challenges we have when working with routers is that there's only one best route to a different location. If you were to look at the IP configuration of your device, you'll notice that you have a default gateway. That default gateway is your local router that allows you to communicate outside of your local IP subnet. But you'll notice that there is only one IP address available to list as the default gateway. You can't list multiple gateways in that list, and this brings up a challenge, especially when you'd like to have redundant routers on a single network. One way to provide redundancy, even though you only have places for a single default gateway, is to create a virtual IP address for the router that's in use. We refer to this virtual IP as a VIP, and the idea is that if the primary router disappears, we can move that virtual IP to another router on the subnet so that you don't have to change everyone's workstation to maintain the uptime and availability of the network. This means you as the end user may have no idea how many different redundant routers might be on your local subnet. And if the primary router on your network was to fail and the virtual IP address was to move, you would seamlessly continue to have connectivity using that redundant router. Here's how this would work. You as the end user would communicate to a router or a default gateway on your network, and that default gateway gives you access to other subnets or allows you to communicate out to the internet. In this particular example, we're going to use the First Hop Redundancy Protocol, or FHRP, in conjunction with a virtual IP address that we've associated with Router 1. This is our active router. Also on this same subnet is a standby or backup router. That's our Router 2. Our default gateway is going to be associated with the virtual IP address that we've got associated with Router 1, and that means that all of our traffic will flow out of our network through Router 1. If Router 1 was to fail, there would need to be some type of method to fail over to Router 2. But Router 2 has a completely different IP address. In this configuration, Router 1 and Router 2 are always in communication with each other, but if Router 2 suddenly realizes that it's not able to communicate with the active router, it then removes that as the active router and becomes the active router itself. Then it takes control of that virtual IP address so that everyone on the network is now able to communicate out to the internet through Router 2 using that original virtual IP address. All of the traffic will flow just as it normally did, and the end user has no idea that it's now using a completely different router to be able to perform that communication. Another interesting characteristic of switches and routers is that you can assign multiple interfaces to a single physical interface. We refer to these as sub-interfaces. So even though there might be a single Ethernet interface on a router, we can take that single Ethernet interface and separate it into multiple virtual interfaces. For example, we might have a trunk connection that has multiple IP subnets connecting to a single physical connection. But we may need to reference each individual VLAN in a trunk with a separate IP address on our router. We do that by assigning that physical interface with an additional parameter called a sub-interface. So although the physical interface on that router is referred to as Ethernet 1/1, you would have separate sub-interfaces within that physical interface that might be called Ethernet 1/1.10, Ethernet 1/1.20, and Ethernet 1/1.100. This means that we can set different configurations for each of these sub-interfaces so that we can reference them with the appropriate IP address for that VLAN. Here's how this would look on a network configuration. You can see there are 3 devices. All 3 of these devices are in separate VLANs. There's the red VLAN, the green VLAN, and the blue VLAN. And of course, they're connecting to separate physical interfaces on a switch. The switch then has a single cable between the switch and the router, and it's trunking each individual VLAN within that single gigabit connection. On the router side, we've configured 3 sub-interfaces for that Ethernet connection. Sub-interface G0/0.1, .2, and .3. And then we can assign IP addresses, subnet masks, and have completely different routing tables for each of these individual sub-interfaces as if they were physical interfaces on that router. There are many devices connected to the internet. Some estimates are 20 to 30 billion, and by the time you watch this video, it's probably, of course, going to be more than that. One of the challenges, of course, is that IP version 4 only supports 4.29 billion addresses, and we have completely exhausted our list of IP version 4. There are no more addresses or subnets to be handed out. So now we have to find some way to communicate across the internet to these billions of devices using a protocol with a relatively few number of IP addresses. The way that we're able to make this work is through a technology known as Network Address Translation, or NAT. We often refer to NAT as being the way that we are able to extend the functionality of IPv4 and use so many different IP addresses, but NAT can be used for many different use cases. We just in this video happen to be talking about one of the most popular use cases where we are able to translate IP version 4 from a private address to a public address. If you wanted to get more details on the difference between a private IP and a public IP, you'll want to look at RFC 1918, which defines these different ranges of private IP addresses. These are IP addresses that are not routable on the public internet, so we most often use these inside of our homes and inside of our businesses, and we'll perform translation if we ever need to communicate out to the internet. Certain ranges of these IP addresses are probably already familiar to you. For example, one IP address range that is private is 10.0.0.0 through 10.255.255.255. In a large enterprise network, this is probably the IP address range that you're using. This RFC also allocates 172.16.0.0 through 172.31.255.255. And if you're using network address translation at home, you're probably using the IP address range of 192.168.0.0 through 192.168.255.255. So how are we able to take these private addresses, which we already know we cannot route across the internet, and somehow we are able to communicate to these internet connected sites?
One more.
We are able to do this using network address translation. Let's take this example where Vala would like to communicate to the Professor Messer web server. Vala's IP address is a private IP address of 10.10.20.50, and Vala wants to communicate to a public IP address of 104.20.19.63. To follow this process, let's break these two addresses out and identify them as the source IP address of 10.10.20.50 and the destination IP address of 104.20.19.63. This packet will first hit a router that is configured with network address translation. This router knows that the source IP address of 10.10.20.50 is an internal IP address, and we can't use this IP address if we want to communicate out to the internet. So this router will change or translate that address to something different. This router already has a list of IP addresses that could be used, and in this case, it's changed that IP address to 94.1.
Boom!
Now we have a public IP address, so now we can communicate directly to the Professor Messer web server. For this web server to communicate back to Vala,
on your right,
it's obviously
on
not
my
going to communicate back
on
to
my
the
middle.
internal 10.10.20 address.
Holy
Instead,
shit.
it's going to reverse those IP addresses, and the source IP address now becomes 104.20.19.63, and the destination IP address is the 94.1.1.1 that was originally assigned by the network address translation router. When this router now receives that packet, it's going to perform the translation again, except in reverse, and modify that destination IP address to be the internal address of 10.10.20.50, which obviously matches the IP address of Vala, and now Vala has received a message from the Professor Messer website, even though Vala has an internal private IP address. With standard network address translation, we are translating from one IP address to a different IP address. This means that if we wanted to have many people performing this translation,
Smurf,
we need
Smurf.
to have many more public IP addresses available. There's a way to make this much more efficient using a different form of network address translation called NAT overload or port address translation or PAT.
Nice, nice. Midlink,
Let's
go
take
do
that
the
same
play.
example where Vala would like to
Beautiful.
communicate to Professor
Back to Enmity.
Vala's IP address is 10.10.20.50, but you'll notice we'll also include
Back to
the
us.
source port number, which in this case
Back to
is
OpenNet.
3233. The destination IP address is obviously the IP address of the Professor
Sorry,
Messer
bro,
web
I'm
server
trolling.
at
Sorry, bro, I'm trolling.
104.20.19.63, and in this case, Vala is communicating to that server over port 80. When that packet is received by the router,
Yeah, we bring it back.
10.address
We bring the
needs to be
boom. That's
translated
what
to a
we.
public IP address.
I think they are
And inside
noobs,
of this
bro. I
router
think they
is a
have
network
FF
address
angle.
translation table that shows both the private address and the public address that it's translated to. You'll notice here that the private address of 10.10.20.50.3233 is converted to
Spanish.
94.1.1.1 with a port number of 1055.
I'm about to
When
hit
that
clip of the year.
translation takes
Clip
place,
it, clip it,
the
clip
IP
it, clip it,
address
clip
is
it.
now a public
Yeah.
IP address, and that's what's received by ProfessorMesser.com.
Oh, no.
Because
Oh,
we're
clip
Oh,
that.
my bad, my bad.
Clip that,
network
clip that,
address
clip that.
and the port number, other devices on this
Complete,
network
complete.
can use the same
Okay, I'm
public
thinking,
IP
I'm
address.
thinking.
For example, let's take another scenario where we have Jonas at 10.10.20.70.
Clip that here, clip that here, clip that here.
For this transaction is 5782. And of course, the destination IP address is the same as the web server with a port number of port 80. When that packet is received by the network address translation router, it knows that that address has not been used before, and it puts that into the network address translation table with a different port number on the public IP address side. So now we're using the same IP address of 94.1.1.
Yes, we live. Yes, we live.
as the public IP, but notice that the port number has incremented by one. This means that we can now have many people on the inside of our network communicating externally to a server.
Slaughter.
Pedophile on YouTube. 0 views all day.
Free in the same broadcast domain. For
Tellement
example,
fait,
when we
free
connect
by me,
devices
didn't
to
follow.
a switch,
And we
all
got
of
some
those
fried
devices are
chicken.
in the same
Who's on the
broadcast domain.
viewers?
In this diagram, we have
No,
one switch
ain't no
on the
one.
left, that's our
One
red
viewer.
switch, and all of the devices connected to that switch are in the same broadcast domain. On the right side is a blue network.
Stars.
This blue network is also
Stars is
on
in the
its own
building.
Stars is
That
in the
one.
building. W
That's one, by
star.
the way.
broadcast domain.
Let's
Because there are
go.
two
Stay
separate
tuned for the
switches,
next
and these
stream.
switches are not connected to each other. No one on the red network can communicate.
Did you see what I got?
with anyone on the blue network.
Look.
The challenges with this configuration, however, is that
I
we
got
have
you.
two devices
I
on
got
the
you a new
red
mouse
network
pad.
and two devices on the blue network, but you can see that there are
You want this
24
one?
interfaces on the front of each of these switches. This means we're running two separate switches with two separate power sources. They're both taking up space within our rack, and we have to manage each of them individually. It would be much more efficient, much easier to manage, and much
Ooh,
less
spicy.
expensive if we could have all of these devices reside on the same physical switch.
Do it.
We can do exactly
Nice
that
work.
and continue to provide that separation between the red
Oops.
network and the blue network on the same switch by using a functionality known as virtual local area networks, or VLANs. The red network is still on its own broadcast domain, and the blue network
Nice.
is on its own broadcast domain, but all of these devices are connected to the same switch.
Ooh, that shit solid. We solid.
On the switch as belonging to either the red VLAN
So
or the
did
blue VLAN.
baby.
Only
Boom.
devices plugged into the blue interfaces would be able to communicate with each other, and only the devices plugged into the red interfaces would be able to communicate with each other. Instead of colors, VLANs are defined by number. So in this switch, we have a VLAN 1, a VLAN 2,
No,
and
all
a
good.
VLAN
I go
3.
back.
We can see that there are devices that are connected to
Easy
interfaces
save,
that are
oops.
configured for VLAN 1, other devices connected to interfaces that have
Let
been
me shut
configured
this
for
nerd up.
VLAN 2, and
Sorry. All you. Okay, all me. Huge play. You no worry, bro. I fix it. You calculated. Huge play. Wow. On my right. On my right. Oh no. Ooh, flip into that bitch. Oh, my balls. Ooh. Beautiful, calculated. Oh no. Maybe my bad. No problem, no problem. Oh no. What a disaster. It's okay, it's okay. They are noobs, they are noobs. Ah, we eat those. Yeah, yeah, yeah. Yeah, we do. Watch that shit. Shit. Whoopsies. Oh, stop, man. Just... Holy shit. That ain't right. That ain't right, cuz. fixed. Forget about it. Forget about it. Oui, mon frère, wow, chat. Anyone knows where my frères are? Chat, anyone knows where's my frères? Squares, rectangles! Holy sh... What the fuck? Nice M&M. Ooh. Maybe you? She... I'm base, I'm healing. I'm get. You. Huge. Me. Huge. Me. Huge. Oh. Yeah. Oof. Wow, M&M with the saves. Oof. Corner. Oh. Stupid boost. You. Middling. Pinel. Peanuts. What the fuck? Ah, hell nah. Shit. Well. Nice. A huge touch. Oh, fuck. Oh. Shit. Winnable, winnable. Fuck you. Get the fuck out of here. Je vais, big, j'y vais. Skate, skate, skate. You. On va heal. Nice, nice. I'm up. I'm up 2 snubs. Got me an ace machine. Huge finish. Huge. Bro, can you give me maybe 1 follower on YouTube? I have 0 viewers all day. Like... Man. Give me 1 like. Oh, huge donk! Chat, W's chat for Mr. Rectangle. Huge donk. YouTube shorts in the big 25? And what's that mean? YouTube shorts is loaded. Boom, Eminem. Are you Eminem? What is game, Eminem?
As a very broad description, a local area network or a LAN is a group of devices that are in the same broadcast domain. For example, when we connect devices to a switch, all of those devices are in the same broadcast domain. In this diagram, we have one switch on the left, that's our red switch, and all of the devices connected to that switch are in the same broadcast domain. On the right side is a blue network. This blue network is also on its own switch, and all of the devices connected to this switch are on their own broadcast domain. Because there are 2 separate switches, and these switches are not connected to each other, no one on the red network can communicate directly with anyone on the blue network. One of the challenges with this configuration, however, is that we have 2 devices on the red network and 2 devices on the blue network, but you can see that there are 24 interfaces on the front of each of the switches. This means we're running 2 separate switches with 2 separate power sources. They're both taking up space within our rack, and we have to manage each of them individually. It would be much more efficient, much easier to manage, and much less expensive if we could have all of these devices reside on the same physical switch. We can do
Ooh, shit.
exactly that and continue to provide that separation between the red network and the blue network on the same switch by using a functionality known as virtual local area networks, or VLANs. The red network is still on its own broadcast domain, and the blue network is on its own broadcast domain, but all of these devices are connected to the same switch. We've gone into the switch and defined each interface on the switch as belonging to either the red VLAN or the blue VLAN, and only devices plugged into the blue interfaces would be able to communicate with each other, and only the devices plugged into the red interfaces would be able to communicate with each other. Instead of colors, VLANs are defined by number. So in this switch, we have a VLAN 1, a VLAN 2, and a VLAN 3. We can see that there are devices that are connected to interfaces that are configured for VLAN 1, other devices connected to interfaces that have been configured for VLAN 2, and still other devices that are configured for interfaces that will only communicate on VLAN 3. This becomes a bit of a challenge when you want to connect VLANs across individual switches. For example, you have two switches in this scenario. One of the switches has a VLAN 100 and a VLAN 200, and the other switch also has a VLAN 100 and VLAN 200. We would like for VLAN 100 on one switch to be able to communicate with VLAN 100 on the other switch and perform the same functionality for VLAN 200. Of course, one of the ways we could do this is to simply connect an Ethernet cable between VLAN 200 on both switches and connect another Ethernet cable between VLAN 100 on both switches. You can tell, however, that we're going to run into problems if we want to connect 10, 20, 100, or even 1,000 VLANs across both of these switches. We can't connect 1,000 interfaces across each of these, so instead we should find a way to connect these switches together by using a minimum of physical connectivity. We can do this by implementing a VLAN trunk. This is also referred to as an 802.1q trunk or a .1q trunk. Instead of having these multiple Ethernet connections between VLANs, we have a single Ethernet connection between these two switches, and you can see that we've configured that interface as a trunk interface. This means that anything sent from VLAN 100 or VLAN 200 across this trunk will be dropped off onto the appropriate VLAN on the other side. So how is the trunk connection able to keep track of what traffic is coming from VLAN 100 and what traffic is coming from VLAN 200? The way we do this is by tagging each frame. This is a normal Ethernet frame. We have a preamble, a start frame,
Fucking
delimiter,
bullshit,
a
those.
destination MAC, a source MAC, a type, a payload, and a frame check sequence. To be able to add additional tags into this frame, we're going to add an additional field right in the middle, right after the source MAC address, and we refer to this as the VLAN tag. These VLAN tags are 12 bits long, and if we're not counting the VLAN numbers that are reserved, we can have a total of 4,094 VLANs that can traverse that trunk connection. This makes the process relatively easy for connecting these VLANs together between switches. Instead of having 4,000 physical interfaces that we are connecting to each other, we have a single interface, and we're simply tagging all of the data sent over that connection. Before there was an 802.1q standard to provide this trunking functionality, there was a proprietary form of trunking known as ISL, or Inter-Switch Link. ISL is relatively outdated at this point, and it's likely that any trunk that you'll ever run into will be an 802.1q standard trunk. Let's see how these trunks will use that tag functionality to be able to transfer data from a VLAN 200 on one switch to a VLAN 200 on the other switch. We'll start with a normal Ethernet frame from a device that is connected to an interface defined as VLAN 200. This packet needs to find its way to a device that is on the other switch on VLAN 200, so that packet will be sent to the trunk interface on the switch. At that time, an additional tag will be added that includes the VLAN 200, and it is sent across that trunk connection to the other switch. The switch that receives that frame will look at the tag, see that it was destined for VLAN 200, it will remove the tag from the frame and send that traffic to the end station. So now we have a much more simplified design. Instead of having a separate cable that's running between switches for VLAN 1, VLAN 2, and VLAN 3, we can have a single Ethernet connection between those two and simply trunk all of the traffic between those switches. When you first configure a switch, there will be a default VLAN for this switch. That means that every device you connect to this switch by default
Nasty.
will be connected to a VLAN. Very commonly, this is VLAN 1 that is defined as the default VLAN. But there's another type of VLAN configuration that you would have inside of a switch known as a native VLAN. A native VLAN is one that can traverse a trunk, but a VLAN tag is not added to any of the traffic going over that trunk connection. So it's common to define a single native VLAN within a switch that will never be tagged as that traffic is sent over that trunk connection. This is because there are some devices that will not communicate over an 802.1q network, and some of the administrative functions within your switches, where switches are communicating with each other, may need to use the native VLAN to perform that communication. For example, management traffic or switch notification messages may use the native VLAN rather than being tagged as a separate VLAN inside of that switch. If you're defining a native VLAN on one switch, you'll need to make sure that that native VLAN is identical on the other switch that you're connecting to. Otherwise, you'll see error messages appear in the log of your switch. Up to this point, we've been describing a traditional layer 2 switch, that is referring to the OSI layer 2 or data link layer, where switches make their forwarding decisions based on the MAC address of an Ethernet frame. But there's another type of switch known as a layer 3 switch that's able to make forwarding decisions based on the OSI layer 3 or network layer of an IP packet. This is looking at the destination IP address and making a routing decision on where that traffic should go. You're effectively taking switch functionality at layer 2 and router functionality at layer 3 and combining both of those into the same unit. With the layer 3 switch, we're not changing the switching process. The switch is still operating at layer 2, and we're not changing the way that a router operates. The routing functionality within this device is still operating at layer 3. But both of these are now combined within the same device, saving space, saving power, and making the administration process that much easier. This means that we can have layer 2 functionality within our switch, where we might have separate VLANs within the same physical switch. But now we can also have routing functionality that allows us to route between those VLANs all within the same switch. This means that we'll need to configure interfaces.
God damn, that shit hard. Yeah.
We refer
Yeah,
to these
some
as
bumping.
SVIs or switch
Holy
virtual
shit.
interfaces. If you have a layer
Holy
3 switch, it may
shit.
not have the layer 3 functionality turned on by default, so you may need to enable that in your switch configuration. Many switches require you to restart the switch once you make that configuration
Oh,
change. And you may be
surf you,
thinking, why
maybe?
don't we use layer 3 switches for everything? Instead of having
Hello?
2 separate physical devices, it seems that having one single physical device would be much easier to manage. And in many cases, that's true, but the routing functionality of a layer 3 switch tends to be less capable than the routing functionality of a standalone router. There is a term within the industry where we tell the switch needs to switch and a router needs to route. When you start combining those devices together, you begin to lose functionality. So if you have a smaller remote site, or perhaps even an internet router at home, you might have this layer 3 switching functionality
Huge
to be
bus.
able to route and switch within the same device. It's very common on our corporate networks to need both data functionality for our computing devices and voice functionality to be able to make telephone calls. Before the days of voice over IP, we would need to run one cable for our Ethernet network and a separate cable for our telephones. Our Ethernet cables would connect to a switch, and our telephone cables would connect to a PBX, or private branch exchange. With the advent of voice over IP technologies, we can get rid of that individual voice cable completely
Yes.
and run both voice and data over the same Ethernet connection. And in many enterprise environments, you have a switch that is on the network, you have telephone that you would connect to the switch, and on the back of
It's
the telephone
Diamond 3.
is an
Stop.
additional
Oh,
Ethernet
shit.
cable for local
Shit.
One of the challenges that comes with adding both voice and data to the same network
Ah, I missed
is that
those.
you now have a great deal of
Oh,
contention
no.
between both of those technologies. Data likes to use a lot of bursty bandwidth on the
Excellent.
network, but voice communication prefers a very consistent level of access.
Holy
If there's
shit.
any type of
Holy
congestion
fuck.
or a lot of usage on the network, this could affect the voice over IP
Oh, I can go up.
communication. None of your phone calls would sound very good. To resolve this issue, we can put our voice communication on one VLAN and put our data communication on the other VLAN. But of course, we're using a single wire to connect both our phones and our computers, so we can use VLAN technologies to do that within that same cable through the use of trunking. This requires you to use a switch that will recognize that you're connecting both a phone and a computer at the same time. But once you're
Holy
using
shit,
the right
god damn.
it's a relatively straightforward process. So now with this switch configuration,
Oh,
we can
no.
assign our phones to be VLAN 200, assign our computers to be VLAN 100, and send all of that traffic to
That's
our
bullshit
switch.
going,
It
so
will
it's,
be able to break those two apart and put them on the correct VLAN for that particular use. This means we can now download as much information as we'd like from our computer while we're on the phone communicating
Eat
with
that
others
shit.
to be able to
Oh,
perform
fuck.
both of those seamlessly. When you're configuring a router interface, switch interface, or an interface that's in your local computer, there are a number of options available. In this video, we'll look at some of those
Shit is.
interface configurations.
Unlucky, unlucky.
We can start with the basic connectivity that we have to the network. When we plug in an Ethernet cable, there are a number of Ethernet settings we need to consider, and two of the most important are the Ethernet speed and the duplex. The speed is obviously going to be how fast this connection is going to run. This might be a 10 megabit connection, 100 megabits, 1000 megabits, which would also be 1 gig connection, 10 gig, or even faster. We have to be sure that this configuration is the same on both sides. So if we have a computer that's connecting to a switch, the speed on both of them has to be configured the same. In many cases, we would set this to automatically configure itself. So you can simply plug in any device and the switch will automatically adjust to the configured speed. The other option we might have available is either half duplex or full duplex. In most cases, this is also set to automatic, but if you do set these manually on both of these devices, you have to make sure that both of them are set to be the same. If you have the speeds mismatched on both sides, the connection will not work at all. You'll never get a link light. But if you mix the duplex configuration, where one side is set to half duplex and the other side is set to full duplex, you'll find the connection does operate, but you'll notice that it is not quite as efficient as it should be. And in fact, you'll have very poor performance if you start putting a lot of traffic over that link. This is why one of the initial configurations we'll look for when we're troubleshooting Ethernet is the speed and the duplex, and make sure that they're the same on both sides of the connection. If those match, then we'll shift our focus to the Internet Protocol, or the IP configuration for that interface. This might be an Ethernet connection, it might be a VLAN config, we might be setting up management interfaces, and all of these will need an IP address, a subnet mask, a default gateway, and perhaps other IP configurations as well. These will usually be values that have been assigned by a network administrator. So we'll want to configure and make sure that the IP address, subnet mask, default gateway, DNS settings, and everything else matches the configuration that we've received from our admin. If this configuration doesn't match what we've been given, let's say we've used a different default gateway IP address, or we put in the incorrect subnet mask, then we may find that we're not able to connect to other IP devices on this network. Fortunately, this is a relatively easy configuration to validate. We can simply look at what we've been given and look at what we've configured in the system and make sure that both of those match. Another useful configuration, especially between switches, would be one for link aggregation. This is sometimes referred to as port bonding. We might see it abbreviated as LAG, or link aggregation. This means that we are connecting multiple interfaces together on these two devices, which normally we would not want to do because we would be creating a loop. But if you've configured all of those interfaces as link aggregation, the switch will interpret them as one very large connection rather than 4 individual connections. So if all 4 of these were gigabit Ethernet connections between the switch, we would configure those as lag, and you now have 4 gigabits of throughput to be able to communicate between those 2 devices. Some switches will support an automatic
God
configuration
damn.
of this link aggregation using a protocol called LACP. This is the Link Aggregation Control Protocol. This allows you to simply configure the interface as LACP, plug in the interfaces, and all of the underlying link aggregation configs will automatically configure themselves between those 2 devices. If you were to capture traffic between these 2 devices, you would see LACP traffic being transferred from one switch to the other. To be able to have the most efficient communication from one device to another, we need to be able to send packets across that will not be fragmented along the way. Since we don't always know what networks are located between the 2 devices, there may be times when our data is fragmented and therefore is less efficient to transfer across the network. Fragmenting a packet tends to slow down the overall communication, and if we lose one of those fragments, then we have to resend the entire frame again. Normally, the determination of the most optimal MTU, or maximum transmission unit, is done automatically when you first connect to a device. But sometimes filtering and firewalls won't allow the automated process to work properly, and you may need to manually configure an MTU on your system. On some networks, we're not trying to minimize the size of our communication. Instead, we're trying to maximize the size of our frames. And one of the ways we can do that is through a method called jumbo frames. Ethernet frames by default are 1,500 bytes in length. If we're transferring large amounts of data, we may want to increase the size of those frames to make the communication that much more efficient. And with jumbo frames, you can increase the size of an Ethernet frame up to 9,216 bytes of an MTU. On many devices, you'll find that they'll use 9,000 as the accepted high end of a jumbo frame. In fact, here is the configuration from my computer that says that I can configure frame sizes on my network to be between 1280 and 9,000 bytes. This means I can transfer a single frame that contains the same amount of information as 6 normal frames on the same network. This means there are fewer packets to have to switch or route through my network, and I can transfer much more in a shorter amount of time. The challenge, though, is all of the devices that are in that communications path must understand jumbo frames. So all of your switches, all of your routers, and the other devices you're communicating to have to also be configured to use these jumbo frames. If there is any device in the middle of this communication that doesn't understand jumbo frames, then they will drop these frames and you won't be able to communicate to that device at all. If you had 2 switches and you connected them together with an Ethernet cable, and then you connected another Ethernet cable to those switches, you would create a loop on the network. This means an Ethernet frame would loop around that particular connection until you disconnected one of those cables. There's no mechanism at the MAC address level to count how many times you've seen a frame. So as these frames are going around this loop, you're adding more and more frames to the network all the time. Those are continuing to go around this loop, and eventually you'll overwhelm the capacities of your switches. This can happen relatively quickly. Once you create a loop in a network, it might be a number of seconds until people start calling the help desk stating that the network is down. Fortunately, this is relatively easy to resolve. You simply go back to the switch where you plugged in that cable, you disconnect the cable, which removes the loop from the network, and now everything is back up and running. But of course, we're not always standing in the data center ready to plug or unplug a cable from a switch. We need some type of automated method to recognize a loop on the network and to prevent those loops from occurring. Fortunately, we have a standard that's able to recognize and prevent loops on a network. This is the IEEE 802.1d standard, one that we call the Spanning Tree Protocol. Spanning Tree can configure interfaces on our switch in a number of different ways. It may configure the switch port to be blocking, which means it's not going to forward any traffic. This is commonly used to prevent loops on a network. If we were to plug in that second cable to our switch, Spanning Tree would recognize that a loop was being created, and it would cause one of those interfaces to be in a blocking state. The listening phase is used by Spanning Tree to clear out existing tables and restart the process. It's going to go through a learning process where it listens to understand where all of the other switches might be and if there might be any loops on the network already running. And then it will configure an interface.
Gang, gang, boys.
Which means traffic can be transmitted through that interface.
Who's watching?
Or we'll
Nobody?
configure an interface to be blocking. We
Like
might also
to
have
use that
interfaces that
W
are
in the chat,
administratively
please.
disabled. Those obviously
Spam some
not
W in the chat, boys.
process. Here's a network that is already running
Yo, we
Spanning
won.
Tree, and there are a number
Oh.
of
Who won?
switches. They're
Blue.
identified as Bridge 1, Bridge 6,
mine you
Bridge 5, and so on. You can see there are 5 of them in this
Why are you
particular
doing this,
design,
though?
and you can see that many of these switches are connected to each other, and if we didn't
STP.
have Spanning Tree running, there would be a loop on this network already. But on this network, we already have Spanning Tree that's operational,
Is that
and it has
STP?
configured a number of different
inshallah.
interfaces. There are 3 different
Okay,
types
so
you can see on the screen.
let me tell you
One
the
is
difference
the
between
root
STP and
port,
UDP.
This is
What's the
interface
difference?
of the
Tell me,
switch
I'll
that
give
is
you a
connected
quiz.
ultimately to the single root
What's the difference
bridge on
between
the network.
protocol
There's
STP
also
and
a
protocol
designated port,
UDP?
Fueling it.
other
So the difference is that
that is not the
STP
port
is a lot
connected
more
directly to the root.
reliable,
And there are block
but
ports. These are
it's
ports where
slower.
Spanning Tree has
So
disabled
STP,
that
you want to use it for things that are very important, like
You can see on this
things
network
that you don't
Bridge
want to lose the
21 has a
connection
block
or
port,
lose the
and Bridge
message along
11
the way.
has a block port,
Whereas
and those have been
UDP,
blocked
it's
so that
less
there is
reliable
not
but a
a
lot
loop.
faster.
If we were
So you're gonna
communicating
use
from
it for
Bridge
something
11,
like
you can
text
see there's a
messages.
single
So
root port,
not
and
like
you can
you know
follow
something
that all the
crazy
way back
important like text
those root
messages,
ports
something
to
that
the
you want to
original
send it
root
fast.
bridge. The
And
designated
it's
ports are
also less
available to be
protected,
able
so
to
it's less
send
encrypted,
traffic.
so the message
In
is
this
less
scenario,
protected.
let's say
That's
that
why
we're on
it's
network
faster.
A,
when
يلا
you
بس
keep
كده
it.
روحي.
communicating with a device on
Okay.
network
Proceed.
M. You can see that we can
Look at my
communicate with Bridge
fucking
6,
chicken
which has a
fingers.
designated port and a root port that allows us access to network M. But what if there is a problem on this network and we lose connectivity between network A and Bridge 6? Now we need some other way to communicate to network M, but as you can see, there is a blocked port on Bridge 11, so we would not be able to communicate.
Oh,
Fortunately, Spanning Tree recognizes that we have this disconnection, and it begins clearing out the existing configuration and relearning the topology of the existing
This sign
network.
held up pretty nice
Spanning
against
Tree
all
has
the
changed
winds
Bridge
and
5 so that
tornado
the root
and
port is now on
rain.
the other side, and it has
It's taking
removed the
forever.
block port on Bridge 11, allowing us on Network A to be able to now communicate all the way through the network back to Network M without having another loop on the network. On many networks, we do talk about enabling Spanning Tree and making sure that our Spanning Tree configuration is turned on inside of our switches, but in reality, these days, we're probably running a newer version of Spanning Tree called the Rapid Spanning Tree Protocol. This standard is the 802.1W standard. In the original Spanning Tree Protocol, it might take 30 to 50 seconds for the convergence process to occur. And on today's networks, that is a very long time to wait without any type of connectivity. With Rapid Spanning Tree Protocol, this convergence process goes down to about 6 seconds, which means anytime there's a disruption on the network, we can be back up and running relatively quickly. Fortunately, this Rapid Spanning Tree Protocol is backwards compatible with the original Spanning Tree. So if you have a mixed set of devices on your network that support one or the other standard, you can run them all at the same time.
Yeah.
The protocol works very similar to
Regarde.
the original Spanning Tree
Comme tu veux.
configuration. It simply
Je vais donner un
operates
bisou.
much faster.
Tu
There are some shortcuts and other
Un bisou.
configuration settings
Oh,
within the Rapid
fini.
Spanning Tree protocol, but it has such familiarity that if you understand Spanning Tree
Pas un gars
protocol,
de Billy
it
Kay.
will be very easy for you to understand
Tu
the
fais quelque chose ou
details
t'as déjà
of
hit,
Rapid
ouais, t'as déjà
Spanning
hit,
Tree
je pense.
protocol.
Ouais.
Comment ça, Jay? Regarde. C'est une nouvelle manette? Quoi?
Je sais pas, j'étais down.
Sérieux?
Ouais.
C'était retarded. On se voit dans l'air.
We've
C'est
become
dans
so
ça, là.
accustomed to wireless networks
Ah,
being
de qui?
available,
Elle
we
a mis
often
ça là, tu
forget
vois?
that
Elle
there's
était
a lot of
fucking
work that
dirty.
happens behind the scenes to
shit.
make these wireless connections. This work is done primarily by the Institute of Electrical and Electronics Engineers, or the
Je suis
IEEE.
dans le gars d'un
There's a
zinc.
committee in the IEEE called the 802.11 Committee That is the committee that focuses on creating worldwide standards for
Vad
wireless
happar det på
networking.
Fallo? Ser
In
Wilson?
the past, we've referred to the standards
Hmm?
name to be
Ser
able to
Wilson
describe
happar
the
det på Fallo?
network. For example,
Oh,
we'll
ouais,
describe
trop de sauce, mais c'est chiant.
802.11
Tårtsås?
Fuck me, c'est me dégoûte d'entrer.
Tårtsås, man.
The IEEE committee realized that these numbers and letters combinations weren't very appealing for most people, so they've also assigned separate names that are a little easier to keep track of. For example, 802.11ac is Wi-Fi 5. 802.11ax is Wi-Fi 6 and Wi-Fi 6E, extended version of Wi-Fi 6, and 802.11be is also called Wi-Fi 7. As additional major releases of the 802.11 wireless standards are released, they will also increment those Wi-Fi numbers, so in the future we should see Wi-Fi 8, Wi-Fi 9, and so on. There are a number of technologies used by 802.11 wireless networking, and the first is the frequencies that are in use. 802.11 commonly uses 2.4 gigahertz, 5 gigahertz, and 6 gigahertz frequency ranges. Sometimes there's a combination of them. You may have an access point that supports both 2.4 and 5 gigahertz, and some access points may support all of those frequencies at the same time. Instead of having to memorize individual frequency numbers, the IEEE has created groupings of these frequencies known as channels. These channels help us easily understand what frequencies we may be using. For example, on this access point, we're using both the 2.4 gigahertz range and the 5 gigahertz range. The 2.4 gigahertz range is using channel 6, which is centered on 2.4